Hi everyone, welcome to another exciting lesson here on Odavig Structure Hub. This is a place where you learn, build, and innovate. Today's structural engineering class, we are focusing on two vital structures that shape our environment and keep things in place. So that is dams and retaining walls. So I'm going to talk about dams and retaining walls. So these structures are more than just concrete walls. They are crucial in water storage, flood control, soil retention, and even preventing landslide in hills terrain. So by the end of this video, you'll understand their type, how they fail, and by the end of the topic, which is retaining wall, you'll be able to know how to keep them stable and how earth pressure, like Rankin's theory, help us design safe and functional retaining walls. Dams and retaining walls. I will begin by defining these two terms, that is dam and retaining wall. What is a dam? A dam is a large structure built across a river or a stream to store, control, or divert water flow of water for the purpose such as irrigation, water supply, hydrostatic power generation, flood control, and recreation. So that is a dam. Retaining wall is a structure designed and constructed to resist lateral pressure of soil or other materials when the change in ground elevation that exceeds the angle of repose of the material. So we'll know later what the angle of repose is. So we have different types of dams. We have rectangular dams. You will see it later. We have trapezoidal dams. Under trapezoidal dams, we have water face vertically and water face inclined. So that is about types of dam. So again, we have types of retaining walls. So we have gravity retaining walls. So these gravity retaining walls, they depend on their own weight to resist the lateral earth pressure. So example of gravity retaining walls, we have mass concrete retaining walls, we have masonry retaining walls, etc. Number two, we have cantilever retaining walls. So this is a reinforced retaining wall. It has reinforcement bars, counterfold retaining wall. And then you have gabion walls and then anchored walls. In your free time, you can do more research about these types of retaining walls so that you may know them better and how they function from each other. So we have mode of failures in retaining walls. Number one, we have overturning. Overturning, it occurs when the wall rotates around its toe due to an imbalance between overturning and the stabilizing forces, or a turning moment due to lateral forces exceeds that due to self-weight of the wall. So this is the effect of overturning or the overturning failure in retaining walls. So here we have the soil retained on this side. So if the pressure of this soil exceeds the weight of this retaining walls, then it means it will overturn this way. So it will overturn. It means the weight of the retained wall cannot sustain the lateral pressure of this earth behind it. So it will fail by overturning. So we have causes of overturning. So number one, we have excessive soil pressure. So it means if the soil behind this retaining wall is greater than the weight of this retaining wall, then it means the wall will overturn. Cause number two, we have insufficient weight. So this retaining wall has a weight. So if there is insufficient weight of this wall, then it means the soil will push this wall to the other side and it will overturn. Number three, you have improper construction. So incorrect placement of blocks, insufficient backfill, or a lack of proper drainage can weaken the wall stability. So if there is no drainage on this wall, for example, there is drainage. So this is the drainage. The drainage also you can have it here. So the drainage is to allow water accumulated in this retained soil to move easily from the soil to the other side. By doing so, there will be little hydrostatic pressure in the water on this soil, which will cause this wall to overturn. Again, we have a poor foundation. So if there is poor foundation in the construction, then the wall can overturn. So what are the prevention for overturning? Number one, we have proper drainage. Number two, we have good construction, proper design, consider surcharge load. So the surcharge load, it may be the soil placed above on these retaining walls, or yes, soil above this retained wall. So this surcharge, you have to consider it when designing the retaining wall. So if you don't consider it, then it will bring some problem in the future. Again, we have regular maintenance. Inspect the wall periodically for signs of damage or instability and address any issue promptly. So we have remediation. We have temporary bracing. You can brace it if you can see the sign of overturning, excavation and rebuilding, and soil stabilization. So number two, we talk about sliding. So sliding, failure of a retaining wall occur when the horizontal pressure from the soil behind the wall overcome the friction at the base of the wall. So this is the backfill and this is the base of the foundation, essentially slipping away from the soil. So this retaining wall will slip away from this soil, so it will move outward. It is meant to hold back. This happens when there is insufficient friction. So this is the friction at the base of the foundation. So if this friction is not strong enough, this backfill, which is soil plus water in it, will push the wall outward. So this happens when there is insufficient friction between the wall's base and the underlying soil, making it a primarily concern in a retaining wall design and stability. So when you are designing a retaining wall, you always check for stability and sliding. So that is number 3. You have the bearing capacity failure. So a bearing capacity failure occurs when the soil underneath the wall's foundation cannot withstand the weight of the soil being held back, causing the wall to sink, or crumble, due to inadequate support, essentially meaning the foundation is not strong enough to handle the load placed upon it. This can manifest as cracks, fracture, or visible soil movement around the wall base. As you can see, this is a retaining wall, and this is the original foundation, and this is the foundation after the effect of weak bearing capacity. So if this foundation is not strong enough, this wall will sink, and this will be the new foundation of the retaining wall. So let's talk about global failure or a deep-seated failure. So this will be the last item on mode of failure in retaining walls. So what are deep failure? It refers to a failure mode where the critical slip surface causing the wall to collapse extend far beyond the immediate area in front of the wall, often reaching deep into the soil behind it, signifying a large-scale instability in the surrounding soil mass rather than just a localized failure of the wall itself. So this is a deep-seated failure. As you can see, this is a slip circle. So this wall have just slipped back on the backfill of that soil. I want to talk about rectangular dams. So this is a rectangular dam. From the name itself, rectangular dams, these are dams which are in the shape or in the form of a rectangle. So they appear as a rectangle. As you can see in this diagram, this is a dam. It is in a rectangular form or a shape, and this is the water body. So this dam is holding back this water body. So I want to analyze this rectangular dam so that at the end we may know where our pressure center is, and also our resultant force is acting at. So under this diagram on the board, we have this symbol H, which is the height of water. So this is H from here to here, is the height of water. And then you have F. F is this force. So it's a force exerted by water on the side of the dam. So this is the body water, and this force is the force as a result of this water acting on this dam. And then we have W. W, as you can see, it is here, and it is a force, this force. So it's the weight of the dam per meter length of dam. So it's a force which is weight of a dam per meter length of a dam. And then you have capital H. Capital H is the height of dam. And then you have B. B is from here to here. That is width of a dam. And then you have WO. That is the weight of a dam. So we will consider a 1 meter length of a dam while analyzing rectangular dams. So I want to begin by this h over 3. So some of you may be asking themselves, where did I got this h over 3? H over 3 is the centroid of this pressure of water on a dam. So in physics, we know that pressure increases linearly with depth. So it means if you have water in a storage tank, so this is a storage tank. Let's say it's a rectangular storage tank. So this is water. So if I can draw a pressure diagram, let me draw it here. So this is a pressure diagram. We know that pressure increases linearly with depth. It means at this surface, at the top surface of the water, the pressure will be 0. And then it will keep on increasing as we proceed to the base of this tank. So it means at the base of this tank, we'll have the maximum pressure. So if I can connect, so here we have 0 pressure. So if I can connect this point and this point, I will end up having a triangle like that, such that the pressure at this base is high than the pressure at the top. So here is 0 and here is high. So if I can draw the pressure itself, so that one will be the pressure diagram. Yes, like that. So this is a triangle. And in structures, to find the centroid of a triangle, so let's assume that is our centroid or our center of gravity. So the center of gravity, as you proceed from the base of this triangle, is always 1 over 3 times h. So we assume this is our h. So this is our h. And from this side coming to the center is always 2 over 3 times h. So in our case, we are moving from this base to where the force is acting. So our center of gravity will be h over 3 from here to here. So that is one thing to note. So let's now analyze this rectangular dam. If I can begin by analyzing this force, I will end up having, so force is equal to W, which is the weight of this water, times area times h bar. But area is equal to this h times, we have said to consider a 1 meter length of the dam. So times length times 1 times h bar. But also h bar is equal to h over 2. So h bar is the centroid of this h, which will be h over 2. So F is equal to W times H times 1 times H over 2. So which imply F is equal to W H square over 2. So that is our F, which is force of this water acting on a dam. So this force F will be acting horizontally, as you can see, above H over 3 from the baseline. So force, which is F, will be acting at H over 3 above the base of water. Like that. So let's proceed to weight W of the dam. This weight W. So the weight W of the dam, the weight will be the weight density of dam, which is WO times volume. So this one will be WO times area times length. So this one is area. So here we'll have WO times area. So area of the dam will be B times H. So B times capital H, then times length. But length of the dam, we have considered it to be 1 meter. So the weight of the dam will be W0 times B times H. So that is the weight of the dam. So this weight of the dam, which is W, it will be acting through CG or GC. So it will be acting, so the weight W will be acting downward through CG, as you have seen on the diagram. So we have only two forces acting on the dam. And which are these forces? We have force W and force F and force W. But the other force, which is R, is as a result of these two forces, force W and force F and force W. So how are we going to determine this force R, which is the resultant force? So R is the resultant force. How are you going to find it? So to calculate or to find the resultant force R, take OC as F. So take OC as F and OB as W. So take OC as F, this force F, and OB as W, and then connect from here to here, and then from here to here, and then intersect so that you can have the resultant force R. So the resultant force R, if you use Pythagoras theorem, you will have OC square plus OB square. Then you get the square root. So which imply R is equal to the square root of OC is F square plus OB is W square. So that is how you get the resultant force R. So let me create more space for analysis. So we have this angle. You have this angle. Let's call it theta. This angle is it has come as a result of this resultant force R and W. So how are we going to get that angle? So if I can draw it here, so this is B, this is O, and this is R. And at this point, we have C. So you know that OC, distance OC is the same as distance BR, which is equal to F. And OB is equal to W. So we are going to use this F and W to get this angle. So if we can use these basics of mathematics, we will have our opposite and adjacent. So we'll end up having tan theta is equal to opposite, which is F over W. So that is how to get that angle theta. So let's extend this resultant force R so that we may end up having here M, and also extend OB so that we may have N, and extend this also this so that we may have distance X. So this distance X, where the resultant force is cutting, can be obtained from similar triangle, which is OBD and ONM, as follows. So NM, so how to obtain distance X? So number one, from similar triangles, whereby NM over ON is equal to BD over OB. So NM is from here to here. You compare with ON from here to here is equal to BD over OB. So our NM is X over our ON. ON is W. Now our ON is this distance from here to here, which is H over 3. So that is H over 3 is equal to BD. So BD is F and OB is W. Yes, like that. Then we make X the subject of the formula. So we'll end up having XW is equal to F multiplied by H over 3. So XW, so which imply XW is equal to, you open the bracket, FH over 3. To get X, you divide both sides by W. So here. So you will end up having X is equal to FH over 3W. So that is our first option. You go to the second option. The second option, you can consider by summing moment at this point M, at this point. So it means you will have two forces, which is force F and W. So let's say second option, number 2, Roman 2, summing moment about point W. So summation of moment at W is equal to 0. So if I sum moment, no, summation of moment at M, not W, at M. Summation of moment at M is equal to 0. So if I sum moment at this point M, I will have this force F in which direction? Clockwise, times the distance, perpendicular distance from here to here. So F times H over 3. This is positive, and then I have this W anti-clockwise, as you can see, anti-clockwise. So we have W minus W times the perpendicular distance from here to here, that is X, times X is equal to 0. So FH over 3 minus WX is equal to 0. So FH over 3 is equal to WX. Then you are interested in the X, you divide both sides by W. So W cancels. So X is equal to FH over 3 times 1 over W. So X is equal to FH over 3W. So that is another way of finding distance X. So example 1, to see my example 1, kindly follow my channel, and to follow you have to subscribe so that you may be updated when a new video is uploaded. So subscribe so that when I upload another video, for example 1, you'll be able to be notified. So thank you for your time.